This is an artificial squirt gun. I'm sure that at some point, if you played with one of these, you take in water or a liquid of your preference and shoot it at people. And there's all kinds of these ones with a handle, like this one, without a handle, bigger ones without a foam cover with cute little rubber duckies on top. And then my personal favorite, I call this one the line deleter. Let's say you're in a supermarket and you're in a line and the line is not moving, you're bored. All you have to do is get your hand, get it just a bit wet, put this away somewhere discreetly, and no more line. That's the primary function. The secondary function is that you can take some water, and then as you move the piston up, it creates a vacuum. If you put it in water and create a vacuum, the water is going to fill the internal chamber, and then you can direct at your target of choice and make the target wet. But what's more interesting than making people wet from a distance is that the only difference between all of these squirt guns that I just showed you and a shock absorber in a car, motorcycle, truck, any vehicle, the only difference between the two is the location of the holes. That's the same thing that actually told me in Bangkok. Anyway, the holes I'm talking about are these holes here on this end at the front and here on the back. If we take these holes from the ends, plug them, and transfer them onto the piston that's inside, this is going to become an actual shock absorber. And I can prove it by doing it right now. First, I'll take some of this sealant from the other side as well. And then I'll seal it with a nut, some washers, and a bolt. That's one hole sealed. Now let's proceed to the other hole. Now we're going to drill 2 holes in the piston. I know this is not the right way to do it, holding it like this. Whoa. Okay, so that's 2 holes in the piston. Next, we're going to seal the shaft against the holes on the back end. I'm going to use this, which is some sort of rubber seal for used in kitchens, found it in a hardware store. It seals against the shaft, and we're going to go to this part right here. Next, we're going to take some oil and pour it into our body of the shock, whatever you want to call this now. I think that's about enough. Then we are going to sink our piston. And finally, we are going to seal the top. And we've just made a shock absorber. And I can prove it's a shock absorber, that it does exactly what its name says. It absorbs shocks. Let me just clear the clutter. Okay, here's an unmodified squirt gun. Here's the shock absorber. And now we're going to expose them both to a sudden, rapid burst of force, a shock. Let's see what happens. As you can see here, the shock is absorbed. Here, the piston bottoms out. A shock absorber and a squirt gun obviously do very different things, but the funny thing is that they work on the absolutely same operating principle. How come?
Well, that's because both oil and water are incompressible liquids, and as such, they must obey something known as the continuity equation, which states that when an incompressible liquid is transitioning from a tube or a pipe with one cross-section to a tube or a pipe with a different cross-section, it must maintain the same flow rate. We can express it with this very simple formula. Now, I know everybody hates formulas, but this one actually makes things easier to explain rather than harder. A is our cross-sectional area, and V is the velocity of our liquid. So if we increase this cross-sectional area, then this speed must increase in order to maintain the continuity equation. The hole at the exit of the squirt gun, as well as the hole we made in the piston, both represent a change in cross-sectional area. Water or oil transitions from the large cross-sectional area of the tube to the very small cross-sectional area of the exit hole or the hole in the piston. Yet it must maintain the same flow rate while it is transitioning. When the cross-sectional area becomes much smaller, it becomes physically impossible to fit the same volume of water or oil through it. So because we can't fit the same volume, but must maintain the flow rate, we are forced to then increase the velocity. In other words, inside the tube, we move a large volume of water very slowly, but at the outlet hole, we move a very small volume of water very quickly. But here's the important bit. The greater the mass of water we want to move within a given period of time, the greater the force that we must apply. If you ever played with a squirt gun, you know that to expel the liquid further, you need to work hard. You need to apply a considerable amount of force with your hand. There are several factors at play here. The first one is, of course, the outlet hole or the nozzle. It is a restriction to flow, and to overcome this restriction, we must apply a force. The smaller the nozzle, the greater the force required to push water or oil through it. The second thing we must overcome is the internal friction or the viscous forces within the water. The greater the amount of water we are trying to move or push within the same period of time, the greater the internal friction, both between the molecules of the water itself and between the water and the walls of the pipe. The greater the friction, the greater the force needed to overcome it. And finally, we have to deal with increasing pressure. Water is an incompressible fluid, which means that when we try to compress it, its volume doesn't really change, but its pressure still increases. And the greater the amount of water we are trying to move through the small nozzle, the more the pressure of the water behind the nozzle will increase. As this pressure increases, it acts against the force of our hand. So we must keep increasing the force generated by our hand exponentially if we want to increase the amount of water coming out. Now, everything we just described and demonstrated for a squirt gun works absolutely the same for a shock absorber. The only difference is that instead of expelling the liquid outside, we move it from one side of the piston to the other. And instead of our hand creating the force, we have bumps or other road imperfections. So the greater the bump and the faster we approach it, the greater the force acting on the shock absorber. Of course, most vehicles are heavier than humans and are capable of moving at much greater speeds, which is why they're capable of producing much greater forces acting on the shocks than a human hand could ever hope. And this is why we use oil instead of water in vehicular shocks. Oil is an incompressible liquid, just like water, so the same physics applies, but oil is far more viscous. It has greater viscous forces or internal friction, which results in greater resistance to flow. So it takes a considerably greater force to get oil from one side of the piston to another than if we were running water. But we can also manipulate other shock parameters to make them capable of resisting greater forces and make them more suitable for a particular application. For example, off-road shocks, due to the very uneven terrain, often have to deal with greater forces. And this is why they're typically going to have a greater stroke. And your stroke is the maximum distance from the top of the piston travel to the bottom. A greater force will push the piston further in. The greater the maximum distance that the piston can travel, the greater the force it can absorb before it bottoms out. Also, a more extreme shock can have an even thicker, more viscous oil and smaller passages, smaller holes in the piston for an even greater resistance to flow, so it can handle an even greater force before bottoming out. So that's the basic operating principle of a shock, but there's something we haven't answered yet. When a force acts on the shock and pushes the piston all the way down, as you can see, we have a problem. It stays down. So how do we get it back up? Well, apparently they have all sorts of tricks for that in Bangkok, but we're not there now. So we're going to use this, and this is a simple spring. When a force is applied onto a spring, as you can see, it compresses. When that force is removed, it springs back up. So what we're going to do is that we're going to attach it to our shock absorber, like so. And then we're going to put a cap on there so the spring stays in place. Now again, let's imagine that we're approaching a bump, and that bump, the force of that bump is again, of course, going to push the piston and the shaft of the shock absorber into the shock body. We're going to absorb the shock, but the force is now also going to compress the spring. And what happens when the bump is gone, when the force is no longer present, when the force is released? The spring is going to pull the piston back up and make it ready to absorb the next bump and the next bump and hundreds of following bumps, and so on with as many road imperfections as you want. The process continues and you ride in comfort. Now, springs do more than just pull the piston back up. They also allow us to carry the weight of the vehicle. If we didn't have spring, the weight of the vehicle itself would actually push the piston deep into the shock body and render it pretty much useless. But springs carry the weight of the vehicle. The fact that they carry the weight of the vehicle and the fact that the weight of the vehicle compresses the springs a bit allow us to do another very important thing. It allows us to keep contact with the road surface when we go over holes in the road and not just bumps. If we didn't have springs going over a hole in the road, the wheels would just fall in. This would greatly compromise comfort, stability, safety, pretty much everything. But because the weight of the vehicle compresses the spring, it means that when going over a hole, the spring can extend to keep contact with the road surface. So if springs are so great, if they can do everything, why do we even need shocks? Because think about it. A spring could compress with big forces, compress more, compress less for smaller forces, extend, and why do we even need the shock and the oil and the piston, all of that? Well, springs are great, but they are still kind of useless on their own. Number one, depending on how the force is applied onto the spring, the direction of the force and how it acts, the spring can move left and right and bend and do other funky stuff. That is 100% undesirable on any vehicle, and that's what the shock and the shaft of the shock prevent. They anchor the spring to the shock body and ensure that the spring can only move, compress up and down in a linear manner without any significant side-to-side movement. The second problem with springs is that when a force is applied on them, when they're compressed and when the force is released and when they extend, they tend to oscillate or bounce up and down. And that is, of course, undesirable because for vehicle occupants, the only oscillations that are comfortable are the ones produced by themselves, with all other external oscillations being undesirable. And it is precisely these oscillations that the shock absorbs. It doesn't just absorb the forces of road imperfections, but also the oscillations of the spring, preventing the spring from oscillating and ensuring a stable and comfortable ride. So as you can see, the spring and the shock, they pretty much make a perfect team because the shock prevents the spring from oscillating, bouncing, and moving side to side and bending, whereas the spring prevents the piston from being stuck at the bottom of the shock body and being totally useless. So that's all of that, but there's still one more thing we haven't talked about, and it is the biggest enemy of all shocks: cavitation. Cavitation can be best described and observed as the formation of air bubbles inside the shock oil, which happens during very rapid piston movement, which can occur both during suspension compression and suspension extension. Now, what happens during rapid piston movement is that the shock oil cannot flow quickly enough through the tiny little holes in the piston, and so it doesn't have time to equalize the pressure across the system. And this means that low pressure zones occur within the shock oil, within parts of the shock oil. When the pressure in these low pressure zones drops below what is known as vapor pressure, air bubbles start to form. Now, these air bubbles are a problem because they reduce the density of the fluid, which reduces damping efficiency, and this then leads to a rough ride and unpredictable handling. But there's another problem, and this one you can actually hear. Let me get it close to the microphone. Can you hear the tiny little crackling? Well, when the pressure actually equalizes, eventually, the bubbles, of course, they collapse. And when they collapse, they create little shock waves. And over time, over thousands of these little shock waves, the shock is going to get damaged and eventually it will fail due to cavitation. So how do we fight cavitation? Well, it's actually pretty simple. We just have to increase the pressure of the air present inside the shock body. Now that we have a valve on the shock, it means that we can pressurize the air inside the shock. And when we pressurize this air inside the shock, we are doing two things. The first and more important one is that by pressurizing, by increasing the pressure of this air inside the shock, we are also increasing the pressure of the oil, because the higher the pressure of the air, the more it tries to press down on the oil. Now, oil is incompressible, the volume will not change, but the pressure of the oil will increase. The higher the pressure of the air, the more the air presses down on the oil. The higher the pressure of the oil, the more difficult it is to get the oil below the vapor pressure, which means that we are reducing or even eliminating the possibility of air bubbles forming and cavitation happening. The second benefit we get by pressurizing the air inside the shock is that it becomes more difficult to compress it further. The higher the pressure of the air, the harder it is to compress it any further and further increase its pressure. But what we are doing all the time is that we are trying to compress this air. In fact, as the piston and the shaft enter the shock body, we are actually compressing the air, because the more shaft length enters into the body, the smaller the internal volume. The smaller the internal volume, the more we try to compress this air. The higher the pressure of this air inside the shock, the more difficult it is to further compress it, which means that this little pocket of air acts like an additional little cushion, helping to absorb the forces acting on the shock and helping to prevent the piston from bottoming out in the shock. One more final thing I'd like to add is that, unlike most of the content you see on the internet nowadays that carries the label "do not try this at home" because it's either dangerous or stupid or both, this is not that. I encourage you to try this at home. Number one, it's super fun. Number two, it's dirt cheap. Everything I got, everything you see on this video, you can find at pretty much any hardware store. I spent a total of, I think, around 15 euros slash dollars slash whatever you want to convert it into to get this whole setup done. The valve is like from an old motorcycle tube. These squirt guns are super cheap. This is from a hardware store. The sealant from a hardware store. Bolts, nuts, you can find that everywhere. The oil I used is motorcycle engine oil because I wanted to exaggerate the effect of cavitation. If you do this yourself, you can experiment with all sorts of oils, anything from cooking oil to actual shock oil, to see how it affects the performance. You can change the size and the number of holes in the little piston. You can do all sorts of things for a very hands-on, tangible learning experience to feel, see, and hear and experience with all your senses how shocks work and how physics plays a role in all of it. So that's pretty much everything for today. I hope you enjoyed it. And as always, I'll be seeing you soon with more fun and useful stuff on the D4A channel.